Hi everyone, in this example we're going to take a look at one of the exercises at the end of section 1.6, and that section covers what are called autonomous differential equations. And so here we're looking at an autonomous differential equation because it only depends on the dependent variable x here. So this formula for the differential equation depends only on x, and there's no dependence on the independent variable t. So part A asks us to sketch the phase diagram and find the critical points. So critical points and equilibrium points, we can use those interchangeably. And so what it means to be an equilibrium point means that these are solutions that remain constant. So they're going to be of the form x equals c. And solutions that look like this, well, their derivatives, therefore, if they're constant, are going to be 0. So the way that we find and identify these critical points, these equilibrium, is we take the differential equation, which in this case is x minus 1 times x minus 2 times x squared. We set it equal to 0, and we solve for x to find these values. And this differential equation is already factored. So really quickly, we can identify we have 3 critical points, 3 equilibrium at 0, at 1, and at 2. And so once we've identified these critical points, we now can go ahead and sketch what is called the phase line or the phase diagram. So what we're going to do with this diagram is first we're going to indicate where our equilibrium are, what are the x values where the equilibrium occur at 0, at 1, and at 2. And so these are solutions that remain constant. And so I know how they behave as time goes on, they don't change. But what a phase diagram, phase line is going to help us identify is what happens to all of the other solutions that start off at other values of x. So for example, if we were to start off with an x value down here, say at minus 1, then we can use the differential equation to figure out whether those solutions are going to go up or whether they're going to go down based on the sign of the first derivative. So we can plug in minus 1 into the formula for the differential equation. And then take a look at what the sign is. And so notice here, this part is going to be negative. This part is going to be negative. That part is going to be positive. So in the end, the derivative is going to be positive. So that means these solutions are going to go up. So I'm going to put a big upward arrow over here to indicate if we have an initial condition less than 0 as time goes on, those are going to head up. And we can do the same for these other equilibriums. So now I'm going to, for these other initial values. So I can pick a test point that falls in between 0 and 1. So let's say something like 1/2. And then I can check the sign of the first derivative at that initial condition. I won't do all of the math, but if I were to plug in 1/2, the first factor is going to be negative, the second factor is going to be negative, and the last factor is positive. So this one winds up having a positive derivative, and so these solutions also are going to head up. Now we can pick a solution in between that starts off between the equilibrium at 1 and at 2. So for example, if x was 1.5, then we can check the sign of the derivative, and plugging 1.5 into the first factor gives us something which is positive, the second factor is negative, and the last factor is positive. So taking their product, we would get something negative. So now I know that these solutions are going to go down. And then finally, the last region that we need to worry about is what happens if we have an initial condition which starts off above this equilibrium at 2. And so in this case, if x were equal to, say, 3, then the derivative would give us something positive times something positive times something positive. We would get a positive derivative, so that tells us that these solutions go upwards as time goes on. And so keep in mind that we've got these equilibriums. These are going to be solutions that don't change as time goes on, and then otherwise, at other initial conditions, those solutions are going to go up or down. In part B, they are asking us to classify the equilibrium And there are three types of equilibrium: stable, semi-stable, and unstable. So looking at the equilibrium at 0, this one is going to be semi-stable, because if we started off close to 0 but below it, those solutions go up and are going to head back to the equilibrium. But on the other side, if we started with an initial condition just a little bit bigger than 0, these solutions are not going to head back towards the equilibrium at 0. They're going to increase and actually head up towards another equilibrium at 1. So therefore, x equals 0, we would say, is semi-stable. Using a similar analysis, the equilibrium at 1 over here, this one's going to be stable, because if we start just a little bit below x equals 1 or just a little bit above x equals 1, as time goes on, all of those solutions are going to head back towards the equilibrium at x equals 1. So that gives us a stable equilibrium, a stable critical point, and then the last equilibrium was at 2, and this one, this equilibrium is unstable, because if we start above 2, those are going to head away. If we start below 2, they're going to head down towards the equilibrium at 1. So this would be an example of an unstable equilibrium. And then finally, the last part, C, asks us to identify what happens if we were to start off at initial condition of 0.5. And so what's really nice about these phase diagrams is now, given any initial condition, I can determine what's going to happen in the long run for that solution. So if we started off at 0.5, because we have an upward arrow, this means as time goes on, our solutions are going to increase, but they're not going to increase up towards infinity. They're going to increase and then start to flatten out as we approach this equilibrium at x equals 1. So for part C, as t goes to infinity, this solution over here is going to approach the equilibrium at x equals 1.